Hey guys, welcome to another algorithms video in C++. In today's video, we'll be looking at some searching techniques. Now, searching in general is a very important topic in computer science. Whenever you are searching some values in a database or you are doing some heavy weighted for loops, there is a high chance that you are searching for some value. You are trying to match some value, whether it's fetching a user from your database or you are training your machine learning model and you are trying to adjust the weights. You are just essentially searching for those weights. It can be path finding, it can be your brute force or backtracking problems where you search for a particular solutions and so on. My point is that searching is very important while programming, not as a whole thing but as a part of solving your big problem. So without further delay, let's get started. So let's start with the very basic technique of searching, that is searching through an data set one after another, one by one, all the elements. So for our container, let's use a vector to store some int. So vector, let's include it here, and we create a simple vector of int. So vector of int, and we will call this array, and it will have some elements like 10, then let's say 5, 3, 7, 4, 9, 2, 8, 2, and 9. We are going to search for let's say 7 in this array. So what we can do is we can simply write a function that will return the index of whatever we are searching in that array. For 10 it will return 0, or for 5 it will return 1, for 7 it will return 3, and so on. And if the value is not present, then it will return us -1, indicating that the value is not present in that array. And what we can do is we can in later programs, whenever we need that value inside that array, we can use that index to find that or to randomly access that element in that container or in that array with basically order of 1 time. So what we can do is we can simply say int linear search. And by the way, this technique is called linear search because we are linearly looking for one after another. So let's say linear search is here, linear search. And first of all, we will pass a reference or constant reference to our vector, because we are not going to modify this by any means, and we don't want to copy the whole data. If the data is very large, then we should try to avoid copying the value. So this way we are not going to copy the value, or we are ensuring that we are not going to modify this value, and we are going to search for a key here inside this array where we are performing linear search. So linear search is very simple. All you need to do is keep first of all track of position, let's say -1, denoting that the element is missing, and then you can simply use a for loop or while loop to traverse through all the elements. I'm using a for loop, but you can use any kind of loop as long as it can traverse, it's fine. So let's say int I equals to 0, and then let's say I is less than our array dot size, so we can traverse to all the elements inside the array, and we just simply increment I, just a typical for loop. And inside this we are just checking for a simple condition: if array's ith element is equals to our key. And if that is the case, then first of all we say that our position is equals to that index I, and also we have found that element, so we no longer need to go further exploring all the elements. So we just simply can break from the loop, and at the end of the function, as it returns our index or our the position of our key, we just simply return our position. And that's all there is to for a linear search. It's very simple, and actually it's a lot of used search technique, because it doesn't depend on the type of data set you are looking at. It will do the job as long as you can traverse through all the elements. So let's just see how it works. So let's see out linear search, linear search, and let's say we want to search in the array for the element 7, and let's search for another element which is missing from that array. Just 1 second. So I will search for let's say 1 here. Okay, so now let's run this. and as we can see in the output here, for the 7 it has given me 3 because it's starting from 0th index, so 0 1 2 3, the 7th index is actually 3, and as 1 is not present, it's returning me -1. Now the main problem with the linear search is that whenever the array size is very big, it's going to take a lot of time because it's going to traverse to one after another element, and for n size of an array, it's going to have a performance of order of n because it's a single loop that's going all up to the n number of elements. So in general, when the dataset is very large, linear search is not a good option. So what we can do to improve our option? There is one way. There are a lot of ways, but there is one way, is that if we provide a simple hint in our search, okay, and in this case what hint I will use is I will use a sorted array. If the data is sorted, we can use a hint that whenever we look at an element and our key is less than that element, we can be sure that the element we are searching is residing previous to the element we are currently looking at, and the vice versa. If the element is greater, then the element we are currently at, the index of that element is going to be less than the element we are looking for. So using this principle, there are multiple search techniques that are implemented, like jump search or interpolated search and so on, but there is a very famous searching technique that uses this search, and it's called a binary search. So let me quickly first of all create our data set here, which is first let's comment this out, and this is our sorted data set now. So vector of int, let's say our array, and this array is going to have some sorted elements. I'm not going to bother it so much, so 6 7 8 9 like this, and then we are going to use binary search on this array to find our beloved 7 and 1. So first of all, let's give the signature. So int binary search. First let's pass our array reference, so const vector of int reference called array, and then we pass our key that we are looking for, and then we give two positions. So one is start, denoting from where we should start our searching, and let's just set it to 0 for now, and end, to denoting till where we need to search. Okay, if we see these values in let's just change this to a comma. If we look at these values in linear search here, then the value of search was 0 and the value of end was array.size. Okay, -1, because I is going to reach to array.size -1 at most, and then it will get out of the loop because array.size is greater than array.size -1. Okay, so what we will do, what is going to be our strategy? So let's say we are looking for 7. What we will do is we will always check the middle element of our array. So in this case, let's say 6 is our middle element of an array, our array, or 5 is our middle element of our array. Okay, whichever it might be, it doesn't matter. Now we will see if the value we are looking for is greater than or less than the value we are currently at. If it's greater than, then we will skip all the elements that are behind our middle element, and we will just look at this sub range. And the same goes if we are looking for 3 and it is less than 5, then we will just skip all these elements and we will just look for this little sub range. Now let's say we have this little sub range, we are looking for 3, and then we once again try to find the middle and we find 3, so we just return that middle value. Or we are, in worst case, we are looking for 2 and 2 is less than 3, so once again we just remove all the elements that are not necessarily, and we search in our newly formed sub array, and in this sub array we can see there is only one element 2 which is equal to our value, so we return that value. If it's not equal to our value and we have reached only one element, then we can be sure that that value is not present in our search, so we can simply just return -1 saying that this value is not present. Now it sounds very complicated, but it's actually very easy to implement in reality. So first of all, what we need to do, what we need to do is we need to find the mid element, and the mid element is nothing but I'm going to find the index actually. So it's just start plus end by 2. So it's the average of our range. Okay, now if we find the element that we are looking for at our mid, so what we will do is we will simply return that element saying that yeah, we have found that key, this is our mid, and it has that key, use this index to find that value, and so on. So I will just simply return TURN mid. But if the key is not present, okay, then what we will do is we will there is some squiggly lines here, I just don't know why. Oh, this is going to be if. Okay, and now if that's not the case, then we will have a else condition saying that else if our array mid is greater than or equals to our key. So if our key is less than our array mid, we will return binary search, and for this one we will be looking for the key in the array, but the range will be from start till the item that is behind the mid. So we are just looking for the items that are previous to the mid element. Okay, because we are certain that our key is less than our array's middle element. Okay, so it should be staying at behind because our array is actually sorted. The condition is that our array is sorted. Now if that's not the case, then it's going to be the opposite. So we will return binary search in our array for the key, but this time we are going to start looking from mid and we will look up to the end. Okay, it's as simple as that. Now only one thing is required here, that is an escape conditions if there is no such element present at all, and that is if our mid is equals to our start. So let's just put it here, another else if. So we'll say else if our mid is equals to our start, okay, then simply return -1. And I think it's going to work same as the linear search, but in terms of performance it's going to skip a lot of elements, so it's actually going to give us a better performance. So just for the sake of output, let's see how we can get the output here. So binary search, and here we pass our array, we pass our key, we pass our beginning, and we pass our end, that is array dot size -1. Okay, as simple as that. And it's not key here, it's actually 7 that we are looking for, so let's give 7 here, and then end line. And let's also look for element that is not present here, our favorite one. Okay, and why array dot size -1, not array dot size? Because there is one less element in that array in terms of index, because end is actually the index, not the number of elements in that array, and as it starts from 0, the highest index is number of elements -1. So as we can see here in this example, let me open this up. Okay, so as you can see here, 7 is actually the 6th element in this array, having the index of 5 because it starts from 0, so it's giving us 5. And for 1, it's not present in that array, so it's giving us -1. But in this scenario, in this case, we just have let's say to find 7, first of all we have looked at 5. Okay, and because it's the middle here, if we calculate, it doesn't matter if it's 5 or 6, as 7 is greater than 5, we have skipped all the elements till 5, and our next sub range was 6 to 9, and then we looked again and we try to count the find the middle. In this case the middle was 7 and it was returned. So even though it was the fifth index, as the array was sorted and we were just eliminating half of the possibilities, we found 7 in just two moves. Okay, the first move was finding this so this 5, and then the second move was finding this 7. So we just found 5 and then we found 7. It's as simple as that. And in fact, where linear search gives you a order of let's say n, big O of n as your time complexity for the algorithm, where n is the size of the input, binary search surprisingly gives us a big O of log n, which is actually far more better than big O of n. Okay, now there are other search techniques that I told you previously that works similar to binary search on sorted data. Some are like jump search or interpolated search. The concept is same. I'm not going to explain those here, but you can just simply search them in internet. But I'm just going to give you a brief overview of how interpolated search works. Let's say you are looking for a particular page in your book. What you do is, you know that the pages are continuous one after another, so there is 1, then 2, then 3 and 4. So what you suddenly do is you try to divide the array in the proportion, open the book in a proportion. If the book page is at the end of the book, what you do is you skip most of the pages and start looking from there. Okay, so in binary search, although we divide the array in equal halves, in interpolated search we just divide the array in the ratio that is favorable to us, giving that these elements, they are distributed in a fixed way, and also they are sorted just like this. So you can use interpolated search in those cases. And in case of jump search, what we do is we can just specify a fixed distance that we want to hop in searching. Let's say we are just hopping from 2 to 4 and then 4 to 6 and 6 to 8, and suddenly we found that the element we are looking for and the element we are present here is less than the element we are looking for is less than the element we are currently residing at. So we are looking for 7 and now we are at 8. So what we will do, we will just go to the previous jump and then we will start linear search from there. It actually is not as good as binary search, but it actually reduces a lot of effort of linear search, and it gives a moderate searching speed. Okay, so we're not going to discuss those things. Those things are as easy as implementing binary search, just these mid varies, okay, in most of the cases. And in jump search, it's just doing binary search, and whenever we are getting greater, we just switch to linear search and so on. So these are the searching techniques that are being used on an contiguous dataset. Now, what do you mean by contiguous dataset? The word contiguous dataset means is that these dataset doesn't branch. Okay, it doesn't branch. If you are searching for a solution in a backtracking problem, and your solutions are going to branch. Okay, your data is not going to be present as one after another like this. They are not going to be continuous, they are going to be branched. And such an example of branched data is trees, and there are some searching algorithms that work on trees, not these kind of linear data sets. And the benefit is that whenever you are searching in a tree, you can use those kind of concepts in finding solutions to your dynamic programmings or your backtracking problems, or in general just you have a graph or something that is not present in a linear way and have a parent-child relationship. You can use those algorithms in order to search the values. Now first of all, let's just have a tree declared here, and also we need to comment this out. So let's just comment these things out, and we'll call this vector of int, and then we will have this called array, although this is a tree. And let's have this tree like this. So 6, then 3, then 8, then 2, then 4, then 7, then 9. Now I am declaring these things in this order because there is a reason, but I don't want to go to that reason. But let's say how we are going to treat this array as a tree. It's simple. The 0th element is the root of the tree. Then it's a binary tree, means every element has 2 children. So 6 has 2 children, one is 3 and one is 8. Now 3 has 2 children, one is 2 and one is 4, and 8 has 2 children, one is 7 and one is 9. If you just ask me to represent it as a real tree, the data will look like this. Just give me a few seconds and I will draw it here. So we have this 6 here, and then below here we have, let's say, our 3 3, and then we have here, let's say, it's very hard to write like this, 8, and then 3 has 2 children, so it's like this, and then we go here down, and it's the children are here. If we look into this, and then 3 has 2 here, 2 here, and another child is 4 here. Okay, like this, and the same goes for 8 and so on. I'm not going to represent the entire tree, but you get the picture. So the first problem that we face is getting the child of an element, because this is actually represented in an array. In fact, most of the binary trees we generally represent them in as array to save a lot of memory, because pointers are actually going to take a lot of time if you just jump from one location to another location in a memory, if the data is not contiguous. So it's better this way to represent in terms of saving some performance for you. Now let's stop talking about those things, and let's start looking at how to search. So search in branched data set. Okay, so the first way is we are going to from the top we are going to go by one after another until we reach the last node, the deepest node or the leaf node, and then if the data is not present in between here, then we go to the next sibling of that node, that is 4 here, and then if the data is not present here, we traverse back and we go to the next sibling, and then we again go to the depth, and so on. So our initial goal is to go to the depth whenever it's possible. The highest depth value is to be reached. Okay, and this kind of searching technique is called depth first search, because our first priority is to find the depth. So we will just simply call it int depth first search. People call it DFS sometimes to make it sound a little bit cooler. So we pass our tree here, so const vector of int reference, just let's call it tree here. Okay, and then we put our key here, and in case of tree there is always a root node, so let's say int root, and for now let's set root to 0, meaning that we are at the beginning of the tree whenever we are calling this function. Okay, in this case the 6 is our root. So it's actually also very easy like binary search. What we do is, first of all, we check that if the root is containing the actual value. So if tree root is equals to key, then we just simply return root, as simple as that. If that's not the case, then we need to get our children. So we have a left child, and if you calculate the index of the left child from the root, it's actually very easy to calculate. It's root times 2 minus 1 and root times 2, but as our index is starting from 0, so we will just have to add a plus 1, so it will be root plus 1 times 2 minus 1. You just calculate it and you will find it. Okay, and the right child, I don't want to waste my time here explaining these things. When we look into trees in detail, we can look at how I am just finding these values. but at now this is going to be sufficient to find our children. Okay, so one is this is our left child, which is one index behind our right child, and as you can see all the left child like 2 is one index behind the right child, the left child 3 is one index behind the right child 8. Here you can see, so it's just one index behind. And if we look for 3 and we put 3 in this equation, we can say that our left child is going to be 2 for our the value of 3, and so on. So let's not just dive in any more detail in here, and let's say we are going to return our result, and let's set result to -1, saying that we haven't find that value. So now it's very simple. Whenever we're doing depth first search, we just want to see if our left child is less than our 3 dot size. That means if our left child exists, it's not nothing else, just we are looking if our left child exists. And if our left child exists, what we want to do, we want to set our result to the output of the depth first search, depth first search of the tree, and this time we are going to search for the key in the left subtree, the root being the left child. Okay, and the recursive function, it will call itself again and again and again to reach to that bottom leaf node and then come back. And for that come back, what we want to do is we want to check if the result is not equals to -1. If the result that is returned here is not equals to -1. Okay, if the result is not equals to -1, that means we have set this result to -1, but the value of result has been changed. So depth first search has actually met this condition, and some children, when it was considered as a root, it found that key to match, and so the value of the result is no longer -1. So what we will do, we will just simply return our result. Now it's very simple, as I told you. Now what we will do is, we have traversed to the left subtree, and if the left subtree is unable to find the value, we simply traverse to the right subtree. So we will put this, copy this here again, but in this time we will just look for the right child subtree, and it's done. So as you can see, it's actually very simple to implement. Okay, and if everything is not working fine, then we just simply return -1. Okay, just to be safe. I don't think we need to do this, but still I don't want to crash this by any means. So let's just have these implemented. So let's say cout, one second, cout, and then depth first search, and we are looking in our array, as we consider this array as an tree, and we are looking for our beloved element 7 and end line, and then we are going to look for our beloved element 1. Okay, so if we run this program, as everything is commented out, I think we should get only 2 numbers as output, and as you can see, first is 5 and the second is -1. Now if we look at 7, this is 0, 1, 2, 3, 4, 5. So 7's index is 5, and then we get -1 for 1 because 1 is actually not present. And if we look in terms of searching, what we did is we jumped from 6 to 3, then we jumped to 2, then we jumped to 4, then we didn't find, then we jumped to 8, and as 8th child left subtree, we find 7, and 7 matches to this condition, and then it returns. But the problem is that, let's say we are looking for a value which is at shallower level, like 3 or 8. We need not go to the depth of the tree to find that value. We can just look at the get the value by looking at each individual levels first. Like we first search at 3, then we first search at 3 and 8, then we search for the rest. Like for here, first we search for 6, then we search at 3 and 8, then we search for 2, 4, 7 and 9 in the next stage. So this kind of search, instead of going through the depth, is going through the breadth of the tree, and that's why it's called the breadth first search. So let's just see how the breadth first search looks. Okay, so let's say int breadth first search, and here we have the same kind of definition. So const vector of int reference called array, then our key, and then our root, and let's set it to 0 for the start of our search. Now these things are similar. If the root is equals to, let's say, our key, then we return root, and then we calculate our left subtree, left child and right child. So I am just going to copy paste here. Let's change this to tree for simplicity. And now what we are going to do is, first we are going to check if the left child or the right child is equals to the key. So what we will do is, we will simply check if left child is obviously less than tree.size, so that our left child's index is not out of our expectation range, and also we check if our tree's left child is actually equals to the key we are looking for, and if it's so, just return the left child. Okay, let's give a space here. Else what we are going to do is, we are going to look for our right child, and if the right child is matching our condition, then we are just returning our right child, just like that. So after 6 we immediately look for 3, and then we look for 6. Now let's go to the next level, and to go to the next level, what we will do is, we will simply do a small trick. First of all, it's very simple. So it's very similar to depth first search, just a little difference. You can use a stack to put all the value. There are different kind of implementation. In one implementation, what you can do is, you can take all the children and you can put them into a let's say into a stack, and then, or a queue. Then you look for their parents, and then when you reach the children one by one, you put into the queue their children, and then you use their children to search. Okay, you can do that, I can show you, but let's do it in a simple way. So we can just set raise to 1, and then what we will do is, we will just do a similar thing. If left child is less than 3 dot size, so if left child exists, what we will do is, our result is equals to breadth first search in the tree for our key, and this time we are looking at the left subtree. And obviously, if our result is not equals to -1, so if we found actual solution, we're going to return that solution, and if we don't find the solution, then we go for the similar process for the right subtree. So just let me copy this lines here, and then let's paste it here. Okay, and just scroll a little, and here instead of LC, it's going to be RC, and I am very much lazy, so I don't want to write repeatedly again and again. And if nothing is going to match, we just for safety return -1. Okay, so this is all about implementing breadth first search. It looks a little bit bigger than the depth first search, but the only difference is that we directly go for searching after finding the left child and the right child, but here we first search at left child and right child, and then go for searching for its children. Okay, and to implement depth first search in another way, what you can use is, you can use a stack to push the children into the stack, and then use that stack to pop out the children one by one, and then traverse through them to search the value. And in case of depth first search, what you can do is, you can use a queue, and you can push the children into the queue, and then use the values, the childs that are coming out of the queue, the nodes that are coming out of the queue, and use those nodes to find the value. So here I'm just going to quickly change this depth first search to breadth first search. Okay, so breadth, breadth first search. And by the way, I am using a plugin called Vim that actually allows me to type this fast. Okay, like there are literally a lot of key bindings that help me to just quickly replace or copy the lines easily, and Vim is actually free. So now if we look, we have the similar output. I don't need to explain this output. The only difference is that the perspective of our search has been changed. Now we have seen how we can optimize our searching patterns by skipping some values when we are doing binary search instead of linear search when our data set was contiguous. Can we do something like that, something better where we can skip the values? Because in these cases, in case of depth first search and breadth first search, they both are going to look at all the elements to find the value if the value is not present, and it is going to take order of n time, just like linear search we were doing here. Okay, just the data is now branched, it's the only difference. Otherwise they are just acting as a linear search, looking at all the elements. But can we skip some elements? Yes, we can skip some elements, given that we have some kind of hint is to what is the arrangement of the elements. And whenever we have some kind of hint on what the arrangement of the elements is, especially in case of AI and stuff like that, what we can do is we can write a searching operation that takes the advantage of that hint and uses that advantage to skip a lot of possibilities. And in fact, these kind of searches, as they take some heuristic measurements as their primary navigation technique, they are called heuristic search. And one of the very popular heuristic search in case of this kind of tree like data sets is called it's actually binary search. In these tree like data sets where they have a certain rule applied to them is called BST or binary search trees. Now here this particular binary tree that I have declared is actually a binary search tree. Why? Because if you look at it, all the children that are left to our root are less than our root, and all the children that are right to our root, the right children of our root, are actually greater. So if we look at 6, 3 is less than 6 and 8 is greater than 6. If we look at 2, 2 is less than 3 and 4 is greater than 3. So we have this kind of a relation here. If we look at 8, 7 is less than 8 and 9 is greater than 8. So this kind of a special tree is called a binary search tree. Okay, or in short BST. And we will call this function int, let's just call it a so we will call this function heuristic, HURISTIC, heuristic search, search BST. But it's not to be it doesn't necessarily be a binary search tree. It can be any kind of data set. As long as there is a hint on what you are doing, you can use heuristic search. For example, you can also consider a binary search as a heuristic search because you have a hint that the data is sorted. Okay, nothing else. So in heuristic search BST, or simply in BST search or binary search tree search, we first of all let's declare the definition. So const vector of int, a reference, let's call it tree, and then we have our int key and our int root, and as usual we will set our root to 0. Now very quickly what we will do is we will check our condition and find our left subchild and right child. So I will just copy these lines here because these are same, so I don't want to waste my time typing these things here, although we waste a lot of time typing things here and there, but let's save some time. And now it's going to be very easy. If we have our tree root greater than our key, so if our key is greater than our root, then that means we need to look at if our tree root is greater than our key, then what we need to do is we need to look at our left subtree. Okay, our left subtree. Why we need to look at our left subtree? Because the key is less than our root, and if we look at here, then 3 is less than 6, so we need to look at 3. Okay, just like that. And also we need to check if actually that child exists. So if LC left child is actually less than 3 dot size, then what we can do is we can simply return nothing else but heuristic search BST in the left subtree. So tree wait a second, so tree, then the key, and then our left child. Okay, just like that. And we can do the same thing for the right child. So here we can see that we are doing this for our right child, and let's put RC here, and if the element is not found, we simply return -1. And actually this binary search tree, when we search here, it's going to take a order of, once again, log n time in order to look through all the elements, because it's guaranteed to skip many elements while it's searching. Especially when the number of element increases, the performance will drastically increase in case of those algorithms that use order of n, log n instead of order of n. Okay, so just change these names to heuristic search BST, and if we run this, we will find the same output. I did something wrong, so I got -1. Just let me check it out, and the error is simple. Instead of looking at left subtree, we were checking for the right subtree, I guess. Just give me a sec, let me check. Oh, and it's going to be greater, because we're looking at right subtree if our key is greater than our root. So now if we run this, we should probably get the right answer, I guess. Yeah, and we got the right answer. Here, as you can see, here 5 and 1, beloved 5 and 1 is written here. Now there are different kinds of heuristic search, like for pathfinding there is A asterisk search or A search and so on. And also in case of BSTs, there are different kinds of BSTs implementation, like AVL trees, red black tree and so on. You can just search them in Google and find out what kind of databases they are using. And basically this kind of BST that I am showing you is used in databases. They actually use MOA BSTs or MOA search trees. The difference is that in case of MOA search trees, instead of having 2 children, there are m number of children, and we go through all those m number of children, and those children they have a link to their siblings and so on. You can just simply check it out, or if you want me to make a video on MOA search trees, how we can search on MOA search trees, or how we actually search data in our databases, our database softwares, how they search their data or they represent their data, I can secretly make a video on that. But this is, I think, all about there is to know for a basic idea of how searching works. So thanks for watching. Hope to see you next time. Bye.